Hey, this is one class you don't want to cut. Networking 101. You know, wireless is a really amazing technology because we really can't see it. We see the effects of it, right? And anytime we're dealing with something that's more effect-based, we have to represent it with math, with numbers, with impossible abbreviations, it seems like. And one of the ones you're probably going to use more than any is dBs. Now, dBs kind of get a little bit tricky, right, because they're logarithmic, and they add together, but only if they're in the same units. And we use dBs everywhere, right? Let me go ahead and show you what I'm talking about here. dBs themselves are not necessarily a number that they kind of stand alone. A dB is in reference to something. So this is a dBm. The M, I'm just kind of putting the braces around it for emphasis. The dBm means that I'm referencing one number to 1 milliwatt. A dBW means that my reference measurement is 1 watt. And this becomes really important because dBs are always a ratio. They're always two numbers that I'm actually looking and manipulating from somewhere. I'm high or low of my reference number that I'm calling out here in this dB measurement. So M's are milliwatts, W's are regular watts. Now, where you're going to use this at is really two places. On a wireless access point, my dBms, I want to use dBms because typically that's what you're going to use the most and see the most out there. And the reason is, especially in an ISM band type of radio, when it comes to 2.4 gigahertz or 5.2 gigahertz, what you're looking at is that you're staying below 1 watt. Anything above 1 watt in most countries requires a license to actually run. So nearly everything that we're going to install as wireless engineers out there are going to be dealing in the milliwatt range or the dBm range. So dBms are going to give you two reference values here on an access point. They're going to tell you what the transmitted power is. So in this case, we're saying it's 14 dBm, and it's also going to tell us what our receiver sensitivity is. Now, most Cisco access points receiver sensitivity is negative 84 dBm. Now, why is that so low? Well, a lot of times what you're looking at is as your signal's going out, you got a whole lot of power. It's blasting that area out, but then as it goes out and hits its target and it's being transmitted back or replayed back, it's going to start out strong and then it's going to get weaker as we go on, or as it deflects off of different areas in multipass or whatever the case may be. When that signal gets back to the receiver, it's a whole lot smaller than what it was when it left. And so what we have is we have what's called a noise threshold or a noise floor. And so if my noise floor is down here, my wireless signal for my data needs to be right up in here so I can discriminate that and determine that, oh, okay, this is my data piece, this is my noise piece. If I drop below this, let's say I'm at 90 negative dBm, then my signal gets lost up here in the noise and the receiver rejects it. It just considers it ground clutter and it just never does process the signal, and then we lose our range. Now, dBs tend to have a little magic to them, if you will. In a dB itself, and I got dBm here referenced, but really any dB, no matter how you use it, no matter what wireless technology you use, the physics of dBs apply this way. Anytime that I add a 3 dB to any number out there, I'm doubling my effective power out of that device. If I, that was the add symbol, if I minus it, then I'm cutting my power in half. So really quickly you can see that 3 dBs really does mean a lot. If I take 10 dB and add to a number, I'm actually increasing or decreasing my power by a factor of times 10. And then if I add 30 dB to any number out there, then I'm increasing my power or decreasing my power by 1,000 times. So that gets pretty important. So if I've got an access point here that's 14 dBm, and I say that, oh, okay, well, I'm going to bump that up to 17 dBm, that doesn't seem like much when you're looking at the range of these numbers, but what it really does effectively is doubles your power out of that access point itself. And same, so when you're picking out your antennas, knowing what your gain is out of that antenna becomes very, very important on how we start measuring how much power we're putting out here. Because in the end, when we're looking at doing this type of stuff, we're the ones that's responsible for where our signal's propagating out. Everybody has equal access to an unlicensed, unrestricted band, so it's our responsibility to make sure we're not bleeding over and keeping somebody else from using that same band, have that equal right of access, as the FCC calls it. Now, let's take it another step. So now we know about access points and we know about receivers. Let's take a look at antennas. So we got our access point here. We're going to connect it with, with a cable, and then let's say we've got an antenna out this side. Antennas are typically measured in what's called dBIs, decibels isotropic. The isotropic power, or the effective isotropic radiated power, EIRP, is measured also in these same dBs. So you can say that that adds this antenna will add 3 dB of gain to my overall system here. Now, mainly now kind of as a point of trivia, I don't see it too much, but there's another measurement that's called dBds. dBds are decibels dipoles. And the dipole measurement for antennas is really a lot more accurate in what you're going to see in real world. The dBIs, the isotropic stuff, this is a mathematical reference. It's impossible to build an antenna that has these measurements, and it's just really for mathematical references here. The real world stuff is a dBd. So what did the regulatory bodies decide to use? They used the one that is really impossible, and it's just how it is, man. This is how it is around the world. Antennas are measured in dBIs, but if for some reason that you get an antenna that has a dBd measurement on there, all you need to do really is subtract 2.2, and you're going to get the equivalent of a dBi. Pretty important. If you ever do this in front of people, they'll think you're a genius. But in the end, it's just really subtracting or adding 2.2 to that number. Subtract it, you get your dBi. Add 2.2 to this number, and you'll get your dBds. So pretty cool, right? Now, system-wide, as I'm looking at measuring this out and putting dBs in action, it actually works like this. It's kind of cool. I've got an access point that is 14 dBm. I'm connecting it up to my antenna, and I say that my antenna output is 3 dB. Now, mathematically, I can add this up and say, okay, that's 17 dBm. 17 dBm means that this access point is now times 2 what it was when it came out of the box, right? But you also have this one last factor in here, and this is called cable loss, right? Your cable loss is also measured in dBms, and typically that depends upon how good the ends are that are connecting this stuff, how good they're terminated out, and then the quality grade of cable in here. Sometimes this can be a very low number, sometimes it can be a very high number, and it also depends upon how far this cable is. You certainly never want to put a cable on and run it 100 feet if you don't need to. You only want to run your cable for as long as you need to, because every foot you add on here, you start losing dBs. And it's very common to see a big long cable that will lose easily 3 dBs, which means that this gain that I did with this antenna has now nulled out, right? Because this effective power here is a subtraction from that number. Any cable loss has to be factored in. And so if I'm losing 3 dB on this line, the only thing I did here was wasted my money unless I'm focusing that signal on here a little bit better. And sometimes that's really what you want to do. You want to condense and consolidate that signal like on a fire hose, right? You sit there and hold the water, it just kind of squirts out. Put a nozzle on, turn it, you can get some more pressure because you can direct the way the water goes. And it's the same way with wireless too. We may want to keep this number, but we want to direct the signal just a little bit better. Now, one very important thing that I've learned over time is that when we're dealing with dBs on this scale, while it's fun to say that the magic number of dBs, and I still watch for it all the time, is that anytime I'm at 3 is half power point, right? Anytime I add 3 to anything wireless whatsoever, my power either goes double or it's cut in half, one or the other. But in practice, that's not the case. You see, everything that we're talking about in here is really done in kind of in a lab, right? These are mathematical references models, and while they mathematically make sense, they're not real good network design without kind of understanding some of the other factors that go into it, some of the outside factors, some of the Fresnel factors, that kind of stuff. So as a rule of thumb, if I'm looking to design a wireless system, I'm going to say I'm going to take an outdoor network and build it out. If I want to increase my range on here, I start at plus 6 dB. 6 dB is pretty much going to come close to doubling what my range is on a device. If I'm indoor, then I'm usually looking at 9 dB gain is what I need in my system to kind of double indoors. Why? Well, because you have all this stuff bouncing. Your signal is very uncontrolled in an indoor environment because, man, it's bouncing off of other stuff. Outdoors, it's a little bit easier because I can get usually a good line of sight. The only thing I'm really worried about is weather, Fresnel zones, that type of stuff. And so it's not as important. And as you can see, 3 dB separates these, half power once again, right? Another magic number. But when you're designing out your networks, mathematically, yes, always keep this in mind that as we're adding this stuff up, but when you're designing your network and you're adding antennas or you're looking to focus and control that, the numbers I look at are the next series up, and that's 6 for outdoors and 9 for indoors. We can get really complicated with this stuff. We can break out logarithmic charts and all that. Man, that's just silliness. The most important thing to remember about dB is to keep your units straight, stay in milliwatts when you're adding this stuff together, and it's going to work pretty good. Don't forget to subtract for your line loss, and you're going to design a pretty solid network.